Differentiate logarithmic functions. Our objective in this lesson is to find the derivative of logarithmic functions. Recall that if f of x equals a to the x, an exponential function, then the inverse of f of x, or f to the negative 1 of x, equals log base a of x, the logarithmic function. Here's a reminder of the graphs of those functions. Y equals a to the x, where a is greater than 1, and y equals log base a of x, where a is greater than 1. Notice they reflect over the line y equals x because they are inverse functions. When a is between 0 and 1, then y equals a to the x is the exponential decay model, and y equals log base a of x looks like that, again, both reflecting over the line y equals x. Y equals log base a of x if and only if x equals a to the y, based on the fact that the exponential and logarithmic functions are inverses of each other. Let's talk about the derivative of log functions by taking a look at that exponential function, x equals a to the y, and taking the derivative with respect to x implicitly. We'll take the derivative with respect to x of the left side of the equation and the derivative with respect to x of the right side of the equation. The derivative with respect to x of x is 1, and the derivative with respect to x of a to the y is a to the y times natural log of a, and using the chain rule, times dy dx. Dividing to get dy dx by itself, we get dy dx equals 1 divided by a to the y times the natural log of a. Now recall that x equals a to the y. So instead of a to the y, we can put x in that spot. So dy dx equals 1 over x times natural log of a. Now this is something that when we know y equals log base a of x, we should immediately be able to skip to dy dx equals 1 over x times natural log of a. So let's make sure that we memorize the derivative of the log function. The derivative with respect to x of log base a of x equals 1 over x times natural log of a. And of course, that's only for x is greater than 0 because of the domain restriction on the logarithmic function. Now, if we take the derivative of log base e of x, why log base e? Because that's the natural log function. That gives us 1 over x times natural log of e. Well, natural log of e is equal to 1, so of course this is just 1 over x. So that leads us to the derivative of the natural log function, d dx of natural log of x equals 1 over x. Of course, that's for x is greater than 0, since there is that domain restriction on all logarithmic functions. Again, these are two derivatives to just memorize and be able to recall and use: the derivative of the log function and the derivative of the natural log function. Let's take a look at some examples. Find the derivative of each function. Number 1, f of x equals natural log of x to the 5th. Now with log functions, we want to remember properties we can use, like the exponent for what's inside the log can be rewritten as a coefficient, and really this can look like 5 times the natural log of x. Then, when we take the derivative, f prime of x, it's just a constant multiple times the derivative of the natural log of x, which we know is just 1 over x. So of course we have a derivative, but we can simplify to 5 over x. Number 2, f of x equals the natural log of x function raised to the 5th. Notice how similar this looks to the example in number 1. The difference is In example number 1, it was only the x raised to the 5th, whereas this time it's the entire function raised to the 5th. So we want to think of this more like it's a composite function, u to the 5th, where u is the natural log of x function that is inside the power function. So when I take the derivative, f prime of x, I use the power rule, 5u to the 4th, and then using the chain rule, times du dx. Substituting back what u is, we get 5. Instead of u, we plug back natural log of x to the 4th times du dx. The derivative of natural log of x is 1 over x. Again, I do have a derivative, but we can clean this up a bit, so why not? 5 times natural log x to the 4th, all over x. Let's find the derivative of this. Because y is not by itself, we must take the derivative implicitly. Implicit differentiation is required here. The derivative of natural log of x is 1 over x. The derivative of natural log of y is 1 over y, and using the chain rule, times dy dx, equals the derivative of 2x is 2. Now I want to get dy dx by itself. 1 over y dy dx equals, I subtract 1 over x from both sides, 2 minus 1 over x, and then I need to get the 1 over y away from dy dx, so I multiply both sides by y. dy dx equals y multiplied to 2 minus 1 over x. And now I have the derivative dy dx. Let's take the derivative of y equals log base 3 of x squared plus 1. Again, we have something inside a log function. So let's simplify this by calling it log base 3 of u. So when I write dy dx, I'm doing the derivative of the log function, which is 1 over u times natural log of the base, 3. But this is the chain rule, so times du dx. Now, where did I get this from? Let's just recall the derivative of the log function. The derivative with respect to x of log base a of x is 1 over x natural log of a. Here, I'm using u, so I have to use u in my derivative. A is the base of the log, 3 is the base of the log, so it's natural log of 3. Now we can replace with what u equals. 1 over u is that inside function, x squared plus 1, times natural log of 3 times du dx. The derivative of the u is 2x. This is a derivative, but I can clean it up a bit, so I will. 1 times 2x is 2x over x squared plus 1 times natural log of 3. Let's find the derivative of y equals log base 3 of the quantity 5x times x squared minus 1 cubed divided by square root of 4x plus 1. This is quite a complicated function here. So fortunately, we have log properties to help us break this down into a bunch of simpler functions. Notice that I'm multiplying a 5 times an x squared minus 1 cubed. So using my property with logs, that when I'm multiplying, I add the separate logs of those. Log base 3 of 5 plus log base 3 of x plus log base 3 of x squared minus 1 cubed. Of course, I can use the other property that the 3 from that exponent can be rewritten as the coefficient. And then I'm dividing by that expression, so minus, I subtract the log base 3 of 4x plus 1 to the 1/2. I'm going to use the 1/2 power instead of the square root because then I can also put that as a coefficient to the log. Now, I do have many more logs, but they're a lot simpler, so my derivative will be much easier. dy dx equals, this is just a constant, its derivative is 0. There are no x's in there, no variables. Plus, log base 3 of x is 1 over x times natural log of 3. 3 is the base, that's why it goes there. Plus 3 times constant multiple, 1 over the inside, x squared minus 1 times natural log of 3, but here I need a chain rule. The derivative of the inside is 2x, minus, again I have a constant multiple, 1/2 times 1 over the inside, 4x plus 1, times natural log of 3, 3 is the base, and using the chain rule, the derivative of the inside is 4. I do have a derivative, but I can clean this up a bit. 0 is not needed to rewrite, so I'll just start at 1 over x, natural log of 3, plus 3 times 1 times 2x is 6x, over x squared minus 1 times natural log of 3, minus 1/2 times 1 times 4 is 2, over 4x plus 1 times natural log of 3. There's a cleaner derivative. Let's take the derivative of y equals natural log of absolute value of x. To do this, I first need to rewrite the function without the absolute value symbols. So I get natural log of x for x greater than 0 and natural log of negative x for x less than 0. So the derivative dy dx equals, when I do each part, the derivative of natural log of x is 1 over x, that's for x greater than 0, and I do chain rule for this. So 1 over negative x times the derivative of the inside, negative 1, that equals 1 over x for x less than 0. Notice that in both cases, I get 1 over x. So the absolute value really doesn't have an effect on the derivative that we already learned. So it's common to just remember and use the derivative with respect to x of the natural log of the absolute value of x is just 1 over x. Of course, that's for x not equal to 0. Thanks for watching.